All right. So here we go. Chapter 18, field size limitation, otherwise known as collimation. First of all, why do we collimate? Anyone?
Reduce exposure.
Reduce exposure, that's one. Right, helps get rid of scattered noise. So some of you have read in advance. That is good. We've probably been talking about this as well as in your other classes, the need for collimation, but at some point you have to have an official lecture on it. So that's what we're going to do today. But let's start off with someone else's perspective for just a second, just to give us a little example.
What we're going to talk about is the one that turns on the light so that you can visualize where exactly your exposure is going to be coming across the patient. So when you hit this button right here, it's going to turn the light on and off. You will also notice that you have crosshairs in here, and that is going to be the center point of your X-ray beam. That's where we want to manipulate the exposure going through the patient in order to get diagnostic quality done. The last two set of buttons or knobs that we're going to talk about is going to be your collimator knobs. This allows the technologist to control the size of the light, and basically that is the point of exposure for the patient. So obviously the bigger the light field, the more of the patient's skin tissue is going to be exposed. The smaller the light field, the smaller amount. This is called collimation, and we collimate to the size of the body part that we're trying to make a radiographic image of.
So it is a little confusing. I've mentioned this before. When someone says more collimation, that actually means that the field size gets smaller, right? Not bigger, right? So when people say you needed some more collimation, your clinical instructors tell you that next semester, it doesn't mean open it up, right? That would be the opposite. And the point where the lines are, notice on this image, it's just a single line. And in the video, it was like two double lines, right? But that's the point where your central ray is theoretically going to be, which we talked about last week, being that's where you have the least amount of distortion, right? Which is why you don't want to be off in alignment, because it's going to be like elongating when you weren't actually doing anything to the tube. So why are we doing this? Like you said, mostly to get rid of dose, right? If you're exposing less skin to the beam, then dose is just going to go down. It's pretty much as simple as that. Some guidelines that kind of make sense, but it's nice to see it in writing sometimes. X-ray field size should never be larger than the anatomy of interest, right? Hand X-ray doesn't mean hand, wrist, and part of the forearm. If it's hand, it's hand. But you'll see a little bit later some improper examples of collimation, especially when it comes to pediatrics. That's where things get a little bit more difficult, and they call for a chest, but you get half the abdomen. You get something like a chabdomen. Not so good. And certainly it should never be bigger than the image receptor. And this becomes a little bit more difficult with flat panel detectors too, right? Because usually the rule is you grab the appropriate size image receptor, like cassette, for the object. So if it's a hand, you get a 10 by 12. But when you're in a DR room, you always have a 14 by 14 or maybe even larger flat panel, and you're really forced to collimate, right? I mean, you still need to collimate with a cassette, right? You could have it open completely and then have a small 8 by 10 cassette. But it's not as obvious sometimes when the flat panel detector is underneath and you can't really see the borders of collimation the way you can on a cassette compared to the way you see on a flat panel detector. Here's some bad collimation, right? If they're ordering a chest, you should give them a chest. We'll talk about cropping in a minute, which is not a good thing. Some people are just afraid to collimate. And I think it's a skill and even an art. We'll talk about that a little bit more in a minute as well. So cropping is not so good, okay? And unfortunately, you might see that because a lot of technologists out there are doing it. That doesn't mean it's right. So cropping, technically defined by the white paper on the ASRT that I shared with you guys a couple of weeks ago, refers to removing or eliminating information, excuse the typo, by electronically changing the field of view, right? And it should not be used, this is the key point, should not be used as a replacement for pre-exposure collimation, right? So the idea is not shoot the map and then isolate Texas, okay? It's just get Texas, right? When this happens, there are a bunch of ramifications, right? If you're using this in lieu of collimating, right, which you should not be doing, some of the anatomy is removed. In my class in particular, I might not put this overall at the top of the list, but your exposure indicator is going to change, right? Also, the image size will be displayed differently, right? Which can confuse some people. But really the most important part, which kind of steps a little bit out of my scope in this particular course, is it becomes a medical legal issue, right? In that if you crop out information that cannot be recovered by the radiologist, unless maybe they do some kind of magic, but they don't even know it's there to recoup that information sometimes, you are making a medical decision that is beyond our scope of practice. So it's just a no-no, right? Interestingly enough, when you have collimated and you left the field open a little bit too much, they are still responsible for reading, the radiologist, everything that is on that image, right? So if you crop out something, then you are making a decision that's not your decision to make, right? Yes, it might look prettier, but if you have proper alignment, central ray, collimate appropriately, that's where the art form comes in, and it really should be your best practice to really not crop. We never had cropping before, everything was fine. Some of the devices out there, you may see them around. This kind of looks like something that they have in the dentist's office, but actually the theory here was a guy, dentist actually, named William Rawlings. He created some filter type devices that would alter the beam geometry. So what this is doing here is, in a sense, it's collimating, but without moving the shutters. We'll talk about that in a minute. To this area here. In this case, this is an image of a cone. The diaphragm is like a cutout, like a puzzle piece. And if you remember one of the labs that we did not too long ago, where we actually took two exposures, one open collimation, one closed, you saw the increase in what? What went up? What's that? Sharpness? A little bit more contrast, right? Because the noise goes down because you're getting rid of some of that scatter, right? Remember, the scatter is divergent. So this is kind of like, if your scatter is kind of the aura around the sun, you're cutting it out with this kind of cylinder. So you still see some of these around, and they'll fit on the end of the tube. Let me kind of skip one here, and they'll give you a picture like this, right? Where it might look better on your screen when you look at this at home, but the idea here is that your contrast goes up. And the spatial resolution generally stays the same, but it now appears better because it's not being covered up by sort of a fog or noisy area. So it gets rid of some of the noise, which increases the contrast and makes the spatial resolution visibly look better. Not increased, but just looks better. To go back, sorry to jump around a little bit, the diaphragm is just kind of like a cookie cutter, right? It's a particular shape. You don't see them all too often, maybe in certain specialized X-ray units where maybe they're just doing feet or they're just doing wrists. You have a lot of that kind of stuff at HSS where you have a room that's literally dedicated to a particular examination, right? We try not to do that here. We want our rooms to work for a lot of different things, and most hospitals do as well. But some rooms are very, very specialized, right? Like a room where you're doing feet, the tube goes unbelievably low. You can get that thing way down to the ground. But in a diaphragm would be some type of cutout that isn't exactly in the tube, but will then limit the beam. And the idea here is you're cutting out, again, those peripheral areas of the beam, which is going to give you your penumbra, your area of unsharpness down at the bottom there. Questions? So far, so good? Yeah.
Where does the when the beam comes through the aperture, what happens to the part, to the, I guess not the remnant, what happens to the part that gets blocked? Is it about?
Yeah, it just gets absorbed, right? It never makes it through. It's kind of like aluminum filtration, except better because it actually stops that piece. Yes.
Going by the x-rays that we just saw, does the diaphragm actually contribute to the penetration as well?
Oh, you mean, this here?
Yeah, because like the x-rays that we saw, it was like focused on the slope. We saw
It shouldn't hold that thought because we're going to look at the effect of collimation on the remnant beam in a minute. To answer kind of, no, it doesn't really change that. But you'll see what I mean in a second. So, what makes this tougher and scares a lot of people is now your positioning has to be dead on, right? There's nothing to crop here, right? You just have to be good. Also, I use these cones. We use them for sinuses a lot. And you have 40 inches SID with your sinuses, and the cone is like a foot long. So it would be almost up against the person's head, and it was pretty hard to position. So it took a lot of skill, but the images were definitely worth it. I mean, you have to think that this wasn't something that was developed and then gone 6 months later, right? This stayed around for a while. So most of what we're used to using is a collimator that's inside of a particular box, right? The box, like we saw in the video, has a couple knobs to control your light. We learned on our very first lab quiz that, if you have the proper SID, that these numbers down here mean that you can kind of collimate even without the light. But to make life even easier for us, there are systems that are built with what's called positive beam limitation, or PBL. But we're going to see less and less of this. But first of all, what is it? It's pretty nifty. It's a micro switch built into the bucky, onto the table. You pull that tray out, put in a cassette. Let's say your collimation is open all the way. Now you put in a 10 by 12. It will automatically sense the 10 and the 12 side of your cassette and bring your collimation field to that size. The only problem with this, and you should be aware, and maybe one day I'll have enough clout to fix this, I always thought about it, it actually doesn't collimate about a quarter of an inch or a centimeter less than the size. It only collimates to the actual size of the cassette. So if you were to then process that, you won't actually see the collimation. There won't be evidence of collimation, right? So I never really did understand that. Why couldn't they just tweak it so it gave you a little bit less than the size of the cassette? I don't know. But it's useful. And the reason why I think it's going away is because CR is going away, CR plates, right? Which means if you're just using flat panel detectors, you have to pay much more attention to your collimation, right? Like we said before, 1 for dose, but 2, it'll change the magnification, right? Did you notice that the more you collimate, the more magnified the image is, right? And the opposite is true, right? If you do a hand on a 1417 CR cassette, it's going to look like a baby hand, right? With film, you never had those issues, right? Film, the magnification of film only happened when you changed things like SID or OID, but there was no change just because of the size of the image receptor. So here's an example of, she's probably like a grandma because she's been in Merrill's for a long, long time. But we really should be at least 1/2 inch or about a centimeter of light beyond the edge of the anatomy. So, I don't want you to go off the deep end and collimate too much, right? You don't want to cut anatomy. You need to still show the soft tissues, right? You don't want to be like super tech and do a spine. I've seen a few spines, AP spines, where the transverse processes are cut because they collimated too much, right? That's no good either. Because then what does that mean? That completely defeats the purpose, because now you have to do a repeat, which means you've just doubled the exposure. Actually, a little bit more than double, because now you open up your collimation a little bit. So about a centimeter, but really, you should collimate more than that if you can, right? And you really want 4 sides, right? Because you need to have evidence, right, that there was some kind of collimation, right? If you don't see it, you can beg and grovel to your instructors and say, but I collimated. Where? Now, I don't want to go off on too much of a tangent, but there are some systems that'll automatically shutter things. And they'll take the white area around the collimation and turn it black, which makes it easier for the radiologist to see, because it's not as contrasty when they're looking at the images. But one of the first things I learned how to do, and instructors should, is know how to revert back to the unshuttered view so that you could see the collimation. But then if it's not there, then you can grovel more, and it's still not there. I'm assuming this is the lead apron here, which we also need. So yeah, we don't want to repeat because you cut the anatomy, right? That's too much. That really shouldn't happen anymore. There's an image, I think it's coming up over here. I'll go back again. But there was a time where, you had to put multiple views on one cassette. We'll come back to this in a second. And when you did that, you could easily make a mistake and kind of have one part overlapping on the other. And this took a lot more skill. So it should not be nearly as hard to get any one of these 3 views on one cassette. And that's the rule now. Some of it's changing because they're creating different algorithms. But when CR first came out, when DR first came out, well, DR is still the same. It was 1 exposure per view, per image receptor. You couldn't take, I remember doing 3 views of a wrist quite commonly in 3 little squares of collimation. And I used to feel good when they all had, their own 4 borders of collimation around them. None of them were overlapping. One of the reasons we don't do that now is your exposure indicator goes crazy. And it's really a digital issue more than it is, we're just making it. It's not about saving film the way it was, right? Back in the day, I hate to say that, right? The idea was you put multiple views on one piece of film instead of using 3 pieces of multiple films, and you saved some money.
Processing time.
And processing time, for sure. Yeah, when you had a 90-second processor. So repeating is not good, and hopefully that's happening a lot less because you actually cut the anatomy, right? But the modern collimators, they have a little light bulb in there, right? They're kind of hard to get to, and there's proprietary screws just to get to them. But they are made of 2 leaves, right? Of either thin lead or a combination of aluminum that doesn't allow the radiation to penetrate. So more than your 2.5 millimeters of aluminum that we have in filtration. And they call them a double aperture collimator. So you have 2 sets. So you have a first set and a secondary shutter. And this is basically designed to really try to eliminate any kind of radiation that's considered secondary or off focus, right? Anything that's not really going straight through is going to get hit by one of these sets of leaves or shutters inside the collimator. Okay. And it turns out, right, this particular system can cut out about 25% of, what you might have with just one set of collimators. And off focus radiation that kind of coming in at a weird sort of angle can cause some ghost images, right? And even in a digital environment, that can't be fixed, right? Same way that some of us this morning saw that you can't really fix motion, right? Post exposure, right? It's either there or not there, right? The sharpening algorithms just haven't gotten that good yet. Right, so the off-focus radiation are photons that are produced kind of a little bit, think about it a little bit to the side or adjacent to the actual focal spot. So they're still going to create another set of radiation, but now picture it kind of like you have your triangle of divergent beam. Now imagine that you had tracing paper and you traced that triangle, but you were off just a little bit, and then you have that like secondary line. So that's where you can create a secondary ghost image. So, major area that collimation helps us with is getting rid of scatter, right? So when we get rid of scatter, and in the digital environment, scatter equals noise. And we've already discussed that, well, noise is bad, but the opposite of noise is contrast. So if we can have scatter go down, if you like arrows, scatter down, contrast up, right? So between that, so scatter, getting rid of some of the scatter will not only increase our contrast, but it'll also reduce our dose. In addition, we're also exposing less skin, like we mentioned right at the top, and that's going to give us less dose. Our radiation intensity is going to go down. If we're killing more photons, we have less photons, right? And if you have time, right, you guys already know that when things show up in blue, they're usually linking somewhere. So you can read about an article if you want, talking specifically about collimation being an effective dose-reducing tool for X-ray examinations, and they are particularly looking at the lenses of the eyes, right, and doing some analysis there. Right. So if you find yourself bored, don't just watch TV, read more about collimation. All right. So like I said earlier, the spatial resolution doesn't particularly get better. But if we reduce some of the noise, that noise is kind of like a blanket, right? Which will help us visualize the spatial resolution if removed, right? So it might appear that the spatial resolution visibly increases. The major aspect is contrast and dose. There's no downside to collimation, right? A lot of things we talk about, one thing goes up, the other goes down, and there's some kind of trade-off. The only thing that can go wrong with collimation is if you cut anatomy that you shouldn't have cut by over-collimating, right? Let me tell you guys a quick story. I walked out on a temp job once, right? So collimator light was broken. So I go to the doctor. It wasn't a radiologist, just like a doctor that worked in the place. And I said, what am I supposed to do here? Just open it up, they told me. Really? Just open it up and, kind of use your finger and figure out where it is. And so I have kids now, so I don't know if my decision would have changed. I didn't need as much money as I might. But In all seriousness, no, I think I did the right thing, right? And the temp agency, they were cool with it. So my employer, who wasn't that actual office, it was a temp job, they were okay with me walking out, right? Because you don't just leave it open, right? That is unethical. But so this image is up here again, and I know I showed it to you before, but these were the days where you had to work a little bit harder because you had to not only collimate one image, but you had to collimate three. And you used to have to take your cassette. I don't want to get too historical, but there were little notches, and you had to kind of visualize, a cassette in thirds, and then try to make it all match. And they're coming back to this because there are algorithms now. Because I remember when CR first came out, people were like, "Are you kidding?" Because they were used to doing this. I have to use three big cassettes to do 3 views of the finger. So I think there are now algorithms that allow you to do this again, right? But you still have to be very careful because the indicators, the exposure indicators will go crazy when you overlap because this is more stuff for next semester, but the systems are designed to look for the borders of collimation and they're only looking for one border unless there's an algorithm that knows you're doing like multi-view, right? And then it might be looking for more than that. But in most cases, you have to find out from your department and basically what everyone else is kind of looking at. So what we have here is sort of an indication of how you are not, by collimating, digging into anything that's actually important. You're not affecting the main primary beam. You're affecting the diverging beams that lead to elongation and penumbra, that blurring effect on the edges anyway, right? So anything that was here, this image is just not going to look as good, but you're not affecting the percentage of primary beam that's kind of uncollimated in the middle. Right? And now this is kind of interesting. And this is, in my opinion, why a lot of technologists don't collimate. And it comes down to they're scared in a lot of circumstances. Let me explain. When you move the tube around, right, if you go up and down, right, the field of collimation changes, right? If you bring it closer to the table, it gets smaller, right? If you bring it away from the table, it gets bigger. But when you place an object in front of the tube, the same thing happens. So let's say you have a really big person. Their belly, let's say, so they're supine, they're closer to the tube, which makes the field of collimation on their body look what? It makes it look smaller. But if you remove that patient, move them to the side, then it opens up and it's where you expect it to be, and your collimation looks correct. So what do you think technologists do? Look small, they're like, so they open it up a little. Okay, they forget all the concepts about it's diverging and it's going where it's supposed to go. Where does this happen in particular? It happens in particular in examinations where their SID might be a little bit off, like a portable chest. So every once in a while, I see a student that has collimated on a portable chest, and I have to say I'm impressed, because unfortunately you don't see it as much as you should. So this particular slide in particular tells you exactly what's happening, right? Essentially, right, I know this is kind of jargonish, right, that the total area of field size coverage is directly proportional to the square of the distance. What does that mean? It means if you have a field of light, right, and your tube is here, if you bring that tube down halfway, that field of light is now quartered. It's 1/4 of what it was before, right? It's much smaller. So how does one get around this fear? I think it takes practice. I think you need to analyze each image that you take and ask yourself after each one, could I have collimated more? Just a little, right? I mean, we're talking about a centimeter, technically. We would love more, but I want evidence. Evidence is it's there or it's not. So if there's a quarter of an inch, then it's there, right? The more sides, the better, of course. I could also tell when your alignment is off, right? Do you ever look at collimation and see that it's collimated on one side but not the other? How is that possible? You can't, collimate one side at a time. Christian?
If the tube is angled, does it throw it off more, or it's still?
Yeah, that throws things off even more, right? When your tube is angled, and we did this in the lab recently when we were doing like the penny on the angle, you could see that the collimation was altered. But I'm not even going that far, right? I'm just talking about perpendicular, beams and parallel, cassettes and things. But people get scared anyway. But I think you have to ask yourself again, could I have collimated more? And then try to, right? Did you have a?
I also want to say that if the anatomy is not centered in the eye, on the receptor, then.
Right, so yeah, that's actually the answer to the question. If you have collimation on one side but not the other, the exact opposite side. So I'm talking about you have collimation here but not here. I'm not talking about the top and the bottom. That means your alignment is off. Right, that's a telltale sign. I mean, is it possible that your collimator is broken? That's doubtful. Most likely it's the alignment. So that's where, getting used to working with a certain SID really helps us because we know what things should look like when they're at 40 or when they're at, a lot of people, they might be big and you feel like you need to open up your collimator, but their lungs are, generally the same size as everyone else. Yes, occasionally people have abnormally or out of the norm range of lungs, for example, on a chest x-ray, but, you can't say that just because they're a big person, right? And the reason why earlier it said at the very beginning, we talked about never having it larger than the image receptor itself. I have seen students have a really big, let's say football-sized patient. They put a 14-17 in lengthwise, which maybe they shouldn't have put it in lengthwise. Maybe they should have put it in crosswise to begin with. And then they have the light field beyond the borders. So imagine there's no PBL in this case that fixes it for you. They're actually beyond the image receptor because the light field still is not even beyond the patient's shoulders because they're so, barrel chested, for example. It's a skill. Okay. So before we get to this, have we been collimating? And how do you know you're collimating well?
Same size.
What's that?
The same size from up to down or side to side.
So you have four sides.
Yeah, each one the same.
But it's also four sides with the anatomy that's of interest, right? It's not just, you don't want to have an image pop up and look at it and just say, oh, four sides. You don't want to just focus on the borders, right? You have to go a little bit beyond that. So here's something interesting. And my picture's up there, but I didn't do this. How do you know your collimator is working? Well, there is a simple test that you can do. What does it require? Cassette. Look familiar? It's kind of like our cassette. You need some pennies. Okay. Now, typically, if your collimator is off, hopefully you'll notice it, but it might take a long time. So occasionally they go in and do QC, quality control, and they'll look to see that it's actually accurate. Right? And one of the ways that you can do this is by setting up what's called the 9-penny test. And don't quote me. I think this is done either every 6 months, right, or maybe or biannually, right? It's not something they look at all the time, but they should maybe look at it more often. So let me show you how this works.
Collimator test in room 3. We have a 10 by 12 cassette at 40 inches SID tabletop. We are collimating now to 8 by 10 inches. Okay. We are placing the pennies at the edge of the light field and one in the light field still by the edge. And we have our 9th penny and the cathode corner of the IR.
To take it and
Okay, don't get dizzy.
like this because
See, object, you have one penny
As you
like
can
just
see,
on the edge and one
the
not.
edge of the penny is right by the edge of the light fields.
So the idea, I wish this would have continued, is that you process this, right? And you can tell if you're getting the penny that's outside of the light field at any one part, then your collimator could be off, right? And then it's our responsibility to not wait and not say anything, right? Because that's going to affect you and that's going to affect everyone. And it's also a problem that could potentially get worse as you go on. Right? So that is what is happening with collimation. Sometimes they call it the 8 penny test because they don't put that other penny towards the cathode side. Yes.
What's the purpose for that cathode?
You know, I'm not sure. I have to look that up. It might have something to do a little bit with the heel effect. You know, I don't, which we didn't talk about yet, where you have a little bit more. Did we talk heel effect? No, anode heel effect is when you have a little bit more radiation on the cathode side of the tube versus the anode. So when I say it's diverging, I've always talked about it as being like equal, but there's actually a little bit more intensity, especially the further away you are from the center. More intensity on the cathode side than there is the anode side. So we have a little extra time. I wanted to do 2 things. One, I'll ask you if you have questions, and then I wanted to give you a quick little discussion about this thing called trajexis. Yeah. Why? You're sad already. You're like, you can't, she's in the front row, so you can't see. She's like, ah. Doesn't even know what it is yet. So collimation, we should never collimate. Collimation is terrible. No, right? What?
Leave it open.
No, wrong. Always collimate. Sometimes it's easier, right? And, you know, technologists try not to just mimic try to take the good from everyone and maybe not so much the bad, right? You know, if you think about non-linear threshold, which says maybe any amount of radiation can cause some damage, whether you believe it or not, if you just think that there might be a possibility, then you really should collimate, because one really never knows. All right, let me stop this.